A very good morning to all of you. So this morning we will focus on radio galaxies and quasars, which are amongst the most energetic objects in the universe, and also among the largest single objects in the universe, which stretches to about several megaparsecs in size. So this is what I've shown over here is a radio image of the galaxy M87, Messier 87, a galaxy which was catalogued by Messier, which Shonu talked to you about yesterday. And what this shows is the nucleus of the galaxy over here, a jet streaming out, and then diffuse lobes of emission. So M87 belongs to the category of galaxies which we call active galactic nuclei. I'll show you images on different scales and also different wavelengths to sort of bring home this picture over here. And what you see over here is a picture of M87, a similar one, the jet over here, diffuse lobes of emission. And these jets are often visible, particularly when the object is relatively nearby, and other wavelengths as well. And this is an optical image obtained with the Hubble Space Telescope. And you can see as you go from clockwise, from here to here to here, one goes in order of increasing linear and angular resolution as well. So right in the nucleus of this source, what you see over here is again the radio core, and then a jet sort of beginning to form and stream out. And you can notice over here that the opening angle over here is quite large, but it recollimates, and then there is a shock over here, and then it goes further on to form these diffuse lobes of emission. As I mentioned a short while ago, that these kinds of galaxies belong to what we call active galactic nuclei. And we will see what the kind of energies they generate and possible sources of energy for these objects as well. This is an image you're all too familiar with now. This is the image of the black hole around this galaxy, M87. The Schwarzschild radius, which was introduced to you yesterday, is about 1.9 into 10 to the power minus 3 light years, which is about 120 astronomical units. The average, 1 AU is the average distance between the Sun and the Earth. And you can see the diameter of the ring is a bit larger. This is the photon sphere, which you can see. And the jet over here, which I've shown you a very recent image obtained with a very large ring, was actually noticed way back in 1918 by Curtis at the Lake Observatory. He noticed a curious ray of light, as he called it, emanating from the nuclear region, and left it at that in the notes in his observations of nebulae. And it was many, many years later in 1954 that the word jet was first used by Wald and Minkowski, who described that this object is possibly coming towards us because they obtained a redshift of this galaxy, and they noticed that O2, that is singly ionized oxygen for Windell transition, at 3727 angstroms, which has a velocity of minus 295 plus or minus 100 kilometers per second, which means that it is coming towards us. So these were the early beginnings of at least recognizing that there is outflow from active galactic nuclei. Now, before I go forward, let me just try and take a step backwards and look at what we mean by active galaxies. What are active galactic nuclei? What are the different kinds of active galaxies? What are the signatures? How do they generate energy? What are the kind of energies involved? So when I use the phrase active galaxies, the question that naturally arises is, what is a normal galaxy? All galaxies to some extent are active. Our galaxies also, as you saw, exhibit some degree of activity. There are there are no jets that we see, but they're huge sort of bipolar emission at high energies, the Fermi bubbles, the gamma rays, and also X-ray bipolar outflows. So there is some degree of activity in our galaxies. But when we use the term active galaxies, we mean that something which is not a normal galaxy. A normal galaxy is one where we can understand the properties of the galaxy as more or less the evolution of its stellar population, the passive evolution of its stellar population. New stars will form, stars will live its life and die, and as you heard several times, that more massive stars live shorter periods of time compared to less massive stars. A sun will have an age of about 10 billion years, but O-type, the massive stars, will have lifetimes in the scales of millions of years. Now, when I talk of active galaxies, they are broadly classified into what are called starburst galaxies and active galactic nuclei, which I just introduced to you a short while ago. What are starburst galaxies? As I just said a little while earlier, that new stars are forming all the time in our galaxies, okay? Particularly in spiral galaxies, to a lesser extent in elliptical galaxies. For example, if you calculate or estimate the star formation rate in our galaxy, it's about a couple of solar masses per year or so. But in a starburst galaxy, that could be even up to about 1,000 times larger. So there's a huge, immense burst of star formation, which cannot be sustained throughout the lifetime of the galaxy. It could be triggered by interactions with galaxies, which leads to more gas coming towards the center, triggering star formation. Here is an image of a starburst galaxy, which is relatively nearby, Messier 82. It's an irregular galaxy, just 12 billion light years away. And you can see that this is the optical image over here. And what you see in orthogonal direction is a combination of X-ray emission as well as H-alpha emission. And you can see an intense burst of star formation in the center as actually gives rise to supernovae, bubbles of supernovae collapse, and they try to go out along the directions of the steepest density gradients, which are along the minor axis of the galaxy. And these have a very important role to play because they can populate the medium with metals if they manage to escape the galaxy. And as you have learned several times in the course of this winter school, that at radio frequencies you can look far deeper and inside. On the right, what I've shown you are radio images of right the central region over here. These are all false color images at the radio frequencies, and what you see is diffuse emission as well as a lot of compact components. The compact components over there, you can observe them with even higher angular resolution, look at their structures, look at their spectra, and you find that most of them are remnants of explosions of massive stars, which are supernova remnants. And you can see the shell kind of structures. Some of them also have fill structures, and some of them are also regions of ionized hydrogen, which are with the massive stars which are formed, ionizes the gas in this vicinity, and you get regions of ionized hydrogen. H2 is ionized hydrogen, H1 is neutral atomic hydrogen. Drawing upon Dipanjan's lecture the other day, I just showed you the spectrum of MET2. Someone asked yesterday about distinguishing between different kinds of emission. One of the signatures is the spectrum, as you can see. This is synchrotron emission, which Dipanjan talked about yesterday. And this is free thermal emission from the gas which is ionized. And what we didn't discuss so far is dust emission, because this gas actually heats up the dust as well, and these are often very strong emitters in the infrared emission. Nissim briefly talked about of distant galaxies where the dust emission, or where you can see it's very strong emission at millimeter wavelengths, but you can see that dust actually dominates the radio emission and even the free or synchrotron emission. At low radio frequencies, there's a bit of flattening, and that is possibly due to absorption of radio emission. So starburst galaxies are not the topic of discussion today, but I just wanted to briefly mention it to introduce you to diversity of kind of activity in galaxies. So we'll focus on active galactic nuclei, and more specifically on radio galaxies and quasars as we progress today. So what are the characteristics of an HA? High energy output, we'll look at the numbers in a little while, just from the nucleus of the galaxy, originating from the nucleus of the galaxy. And the luminosity which it originates can sometimes even exceed the entire normal galaxy. Don't worry about spectral energy distributions right now. And as you saw a little while ago, they often exhibit collimated jets squirting out from the nucleus of the active galaxy, and the velocities with which it comes out can be very close to the velocity of light itself. They often exhibit prominent emission lines, with line widths corresponding to velocities which may extend up to thousands of kilometers per second. In a short while, I will also show you spectra of galaxies to drive home the point about the prominent emission lines. For example, if you took the spectrum of a galaxy like our galaxy, the Milky Way, it will be dominated by absorption lines. Absorption lines, why? Can anyone tell me why absorption lines? Sorry? The dust is there, but absorption lines, because what you're seeing is an integrated spectrum of the stars. And if you take a spectrum of a star, what you'll see, I mean, the exotic stars which have emission lines as well, but the bulk of the stars are characterized by the absorption lines, where the light from the inner photosphere gets absorbed by the cooler outer layers. Okay? So if you see prominent emission lines, That means there is something much more going on than just the emission from the stars. Sometimes you'll also get prominent emission lines because of ionized nebulae, which emit emission lines. But as you'll see in a short while, that the normal galaxy is usually dominated by the absorption lines. Okay? And variability. Variability, that means our sun varies quite a bit at radio wavelength, but optical to a good fortune, the variability is very, very small, right? Less than about 0.5% or so. But a nuclear source in an active galactic nucleus can vary by factors of 2 or 3 over time scales of hours to days. So rapid or strong variability, not only in the continuum emission, but also in the emission lines. Because the emission lines are corresponding to variations in the continuum, right? They are being sort of ionized and then they recombine because of emission from the nucleus. Now, we'll not look at all types of active galaxies. We will focus on radio galaxies and quasars, which is a theme of today's lecture. But in passing, I will also talk about Seyfert galaxies to introduce you to the kinds of AGN that exist, because these were recognized much before radio galaxies and quasars were recognized as active galactic nuclei. And we will look at briefly at some of these properties. What I've highlighted in green will be mentioned only in passing, and our emphasis will be on radio galaxies and quasars. Okay. Now, Seyfert galaxies. As I just mentioned, that a normal galaxy normally will be dominated by the absorption lines, because what you're seeing is the aggregate spectra of the stars. Okay, you may see some emission lines from nebulous regions, but usually it's dominated by the absorption lines. So Fahd at Lick Observatory, he took a spectrum of NGC 1068, a spiral galaxy, and noticed that there were prominent emission lines. And many years later, Slipher at Lowell Observatory showed that the emission lines are similar to those you found in planetary nebulae. Yesterday, Shobham talked about planetary nebulae, diffuse nebulae. These are the outer layers of stars which are shed, low-mass stars like our sun, which will shed its outer layers, and then they actually get ionized by the central star and emit emission lines. And the lines have widths of hundreds of kilometers per second. This is an HST image of a Seyfert galaxy, a much more recent image of NGC 4051. But these objects called Seyfert galaxies really got its name from Carl Seyfert, who actually did a systematic survey of spiral galaxies, a spectroscopic survey, and found that a significant number of them emitted very strong emission lines. Okay? And we will look at the spectra in a short while. Just to give you examples of it, here are the spectra of two kinds of Seyfert galaxies. Now let me introduce you to, because we will keep meeting this again and again during today's discussion, that there are two kinds of Seyfert. We will not worry very much about the intermediate ones right now. Seyfert ones are where you have narrow lines as well as broad lines. Why are the lines broad? Doppler effect. Very good. Because of the motions of the clouds which are emitting it. So that means the higher the random motion of the clouds, the broader your line is going to be, right? Okay, and there are Seyfert 2 galaxies which are just have narrow line objects. Okay, just remember this, because this is something which you will keep meeting today, and these are referred to as type 1 and type 2 objects. Okay, type 1, so type 2. All right. So these have broad lines, broad plus narrow lines, and these tend to have narrow lines. Okay. Right now we are talking only of Seyferts, but you will find that this, as we go along, we will look at it in different kinds of objects as well. Okay. Yesterday we talked about supermassive black holes. Shomuk introduced you to. So can you guess where the broad lines might be originating from? Closer to the black hole, right? Closer to the black hole. So if you were to draw up a schematic picture of where the broad lines might originate, let's look at an active galactic nucleus, which suppose you had a supermassive black hole over here, then your broad line region would be closer to the nucleus compared to the narrow line region. All right? The narrow line, this is just a gravitational influence of the supermassive black hole in it. Right? Okay. So just remember these two kinds of objects. We will keep discussing them on and on. So, and they can occur in all kinds of environments. So they can be relatively isolated, they can be in groups, they can be in clusters, they can be interacting with one another. This is just an illustration to you that both types of galaxies can occur in different kinds of environments, and you can see some of them are actually tidally interacting with one another, so they occur in all kinds of environments. Just to drive home the point of what we have been discussing, to show you a couple of images. This is an image of a normal galaxy, and you can see that what you don't see the prominent emission lines, but you see absorption lines. You occasionally also find galaxies, as I said, with probably H alpha emission when there are a lot of regions of ionized hydrogen. But this is a typical spectrum of a normal galaxy in the optical region of the electromagnetic spectrum. Now, if I go to a Seyfert-1 galaxy, you can see over here the broad lines of H alpha and H beta, and you can see a number of narrow emission lines as well. And when you go to Seyfert-2 galaxies, it is dominated by narrow emission lines. Okay. Now, when galaxies are interacting with one another, particularly, we talked about intense bursts of star formation, which are often triggered by interactions. And then you also see prominent emission lines, and these are effectively from regions of ionized hydrogen. And you can see the spectra visually looks similar, but if you had just the spectrum and you wanted to distinguish between a Seyfert-2 galaxy and an interacting galaxy like this, a starburst galaxy, you would have to do some line diagnostics because the AGN spectrum extends to harder energies, and so the ionization ratios of different elements are going to be different. But just to make you aware of that, but we will not delve much into that. So Seyfert galaxies were the first kind of AGN to be identified. In short exposure photographs, as you saw in the HST image, they have a semi-stellar nucleus, a point-like nucleus in optical images. They have prominent emission lines, and today we know from monitoring that they are variable, the line emission can be variable, the continuum emission can be variable, and many of them have radio jets as well, but not as powerful as the radio galaxies and quasars. So these objects are less luminous in the radio, the Seyfert galaxies, and traditionally they have been called radio quiet. Okay, they're not radio completely quiet, but they're radio weak. But the terminology which is often used in the literature, which is just of historical reasons, is called radio quiet. Okay, but now we come to radio galaxies and quasars. Nissim told you the historical perspective of how radio galaxies and quasars were identified, so I will not delve or spend too much time on that. But just to illustrate to you the importance of how it went about, just a little bit. For example, what I've shown on the left side over here is a survey of the sky at 1400 megahertz with the NRA 300-foot telescope, which sadly collapsed. It started functioning in the early 60s, 62 I think, and it collapsed in 88. And this is an image, relatively sort of poorer sensitivity and relatively coarse resolution, but not as coarse as the early days of radio astronomy. And if you were to plot this as contours, it is these contours which you're going to see. This is just a small part picked up from here, okay? And what is also plotted in grayscale over here is a survey done with a very large array, an interferometer, with an angular resolution of 45 arc seconds. So you can see the resolution is much better. Now what happens is that when you make a survey of the sky in the early days, then if you just saw lumps of radio emission in the sky, there's nothing much you can do about it except to say that I detected radio emission. So to understand what is the nature of the emission, what is giving rise to it, one of the natural things to do is to try and find out, are they associated with any kind of objects that you're aware of? And by this time, it was established that galaxies were external galaxies just like our own, just as Immanuel Kant had actually speculated many years before observations were able to establish that. So when that was done, resolutions are very coarse, so it was very difficult to identify galaxies with very distant radio sources. The reason being, if you look at this object, if you look at this object over here, you can see that when you observe it at higher resolution, that itself splits up into multiple sources, if you don't have enough resolution. Now, if I were to superpose an optical object over here, optical image over here, there may be many optical objects over here, particularly when you go to more distant parts of the universe. So it is very difficult to uniquely identify, hey, this is the object I'm associated with. So in the early days, the optical objects that were identified with radio sources were relatively nearby. Because the angular sizes of the radio source, because the resolution appeared large, and galaxies which were nearby would also have a larger angular dimension in the sky. So if you found them bang on top of each other, you hold your heart in your hand and say, hey, I think this is associated. You can calculate probabilities as well. Okay. Now, it was these early identifications that led to the identification of relatively nearby sources, like Virgo A, Centaurus A, Pictor A, Fornix A, Cygnus A. So these were named after the constellations, and A because of the brightest source over there. Okay. Now, moving fast forward a little bit, when these objects which appeared as just lumps or blobs in the sky were imaged at higher angular resolution, you notice that they consisted of two lobes of radio emission straddling either side of an optical galaxy, and these are called lobes of radio emission, and these emit, as we saw yesterday from Dipanchan's lecture, via the synchrotron process. So ultra-relativistic electrons gyrating in a magnetic field. Okay. For example, just to give you a kind of number, if I had an electron with a Lorentz factor of gamma, say of the order of 10 to the power of 4, okay, it would correspond to about, you can check it out. I mean, it will be about 8 nines or something. So you can see it's very close to the velocity of light, and if electron is gyrating in a magnetic field of about 10 microgauss, you'll get an emission at about a gigahertz or so. Okay, about a gigahertz or so. So just to give you a rough idea. Okay, so and yesterday also Devanjan mentioned about the non-thermal spectrum, and that is because the energy of an electron which is radiating, the higher the energy of the electron, the higher the frequency at which most of its energy will be emitted. All right? Okay. So, for example, if I had a polar distribution of electrons which goes like this, Ne is proportional to e to the power of minus PdE, say NeDE, okay? And I had a spectrum where flux density is proportional to mu to the power of minus alpha. So these would all be polars in a log-log plane. Then alpha would be equal to P minus 1 by 2. You can think about it this way as well, that if I were to plot the spectrum and I had a non-thermal spectrum, there would be just many more electrons at lower energies which will add up to give the emission compared to fewer electrons as you go to higher energies. All right? So there are more electrons at lower energies, and at lower energy, the emission peaks at a lower frequency, and when you add it up, you'll get more emission at a lower frequency compared with a higher frequency. All right? But when you come to the nucleus of the galaxy, absorption effects become important, and there you get flat and complex spectrum. Maybe absorption effects due to both free absorption, where thermal plasma can absorb the emission, as well as the synchrotron source itself can absorb the emission. We'll not get into those details right now. So this is another galaxy which was identified very early on, and what I want you to notice is that these two galaxies look somewhat different, right? The radio structure. Here you see very prominent hotspots at the outer edges. There's a weak counterjet, but a prominent jet over here. Whereas if I look at the next source, I don't see prominent hotspots, but I see diffuse plumes of emission and reasonably symmetric jets. Okay, just keep that in mind. All right, keep that in mind. And these two kinds of objects were cataloged, were actually classified by Bernie Fanaroff, who was one of the prime movers who got this square kilometer array, or part of it, into South Africa. While he was a graduate student at Cambridge, he sort of, with Julia Riley, they developed this scheme, and these two classes of objects are called Fanaroff-Riley class 1 and Fanaroff-Riley class 2. Okay, so let me just go back to this table over here, and I'll just write down RGs as radio galaxies. These usually have narrow lines, so these are type 2 objects, okay? There are a small minority which have also broad lines, but we will look at the global properties now. And these radio galaxies, the radio structure can be classified into FR1 and FR2. So I'm telling you a little bit of the structures because, although it seems a little bit of detail right now, but because they will become relevant for what we are going to discuss later. So FR2, I'll just sketch it for you remind you, they have prominent hotspots, a core and one-sided jet, and here they have diffuse, sort of two-sided jet and diffuse fluids of emission. So just remember this, all right? Okay, now this just sort of illustrates that as well. This gives you two examples of it, and we will try to understand why this arises later in the lecture today, all right? Okay, now quasars, as Nissim sort of pointed out, were another class of objects which were found by trying to find optical counterparts of radio sources. So this was actually, you needed very high resolution. This was one of the largest redshifts of that time, largest distances, as we learned from Tirthankar's lectures as well, and you needed high angular resolution. In those days, when quasars were discovered in the early 60s, that interferometers, the resolutions were still relatively poor. So they had to rely on observations of the radio source getting occulted by the moon. This was a standard technique which was used using the UT radio telescope and gives you, accuracy to better than about half an arc second. So quasars are basically objects which at that point of time appeared star-like in the Palomar Observatory Sky Survey, which was one of the major optical surveys of the time. So this was a bit of a surprising because stars themselves were weak emitters of the radio emission. It took a long time for us to actually detect radio emission from the sun, although today is one of the very strong sources given our sensitivity. But it appears star-like, so it should be weak, but it was one of the very strong sources in the sky, right? So that itself was, was a puzzle, and the name coined was the quasi-stellar radio source, and that is how it got its name, quasar. And you can see over here that there is an optical wisp which was known very early on as well. Oh, sorry, one second. Optical wisp which was known very early on as well, and these are radio and X-ray images which are shown over here. So we have talked about radio galaxies. Now we have to, I'll just put quasars over here, a bit out of sequence, but don't worry. And these we will just see, they have broad lines. Okay, they have broad lines. Okay, and we will try and put everything together, and that is why I've written that on the board to try and keep reminding you. Okay, so if you look at the spectrum of a quasar, this is a spectrum which Nissim also showed you. They're characterized by emission lines which are broad. Thousands of kilometers per second would be the Doppler velocities it corresponds to, many thousands of kilometers per second. Whereas if you look at the narrow lines, which we talked about earlier, they're usually less than a few hundred kilometers per second. So again, as one of you pointed out, that this must be originating very close to the supermassive black hole, all right? The broad line regions. So this is a summary, this is a picture which Shomak left you with yesterday. Now, initially they appeared star-like on the images. But then the question always arose as to what is the true nature of these objects? Because clearly it's not a star. A star is not going to emit prominent emission lines like this. They're characterized by absorption lines. And this clearly establishes extragalactic nature. So the question arose very early on, are these just galaxies with abnormally luminous nuclei? So the luminosity is very high of just the nucleus. You may not be able to see the galaxy around it because of dynamic range limitations. Just as you don't see the stars when the sun is out. Okay, detecting very faint emission is difficult. And the other thing is also resolution, because a typical scene, which Shomak mentioned, is about 0.5 arc seconds or so, even in the good sites, and the image will get blurred and you'll not be able to make out the surrounding galaxy around it. So it had to really wait the advent of the Hubble Space Telescope with resolutions of 50 milliarc seconds and high dynamic range and very clever image processing to really show that wherever you could see a galaxy, you actually managed to see a galaxy. So quasars are nothing but galaxies with abnormally luminous nuclei. Okay? Abnormally luminous nuclei, and they could be spirals, they could be ellipticals, they could be interacting systems. Some of them you find them interacting over here, some with tidal tails as well. Okay? What we have found so far, quasars are radio loud, right? And radio galaxies are obviously also radio loud. So these are two classes of objects which were identified from trying to find optical counterparts of radio sources. Okay, now the question we'll ask ourselves for just a moment is that that I should probably mention over here, which I skipped, that the host galaxies of Seyfert galaxies are spirals. Host galaxies of quasars can be either ellipticals or spirals. Ellipticals or spirals. And the host galaxies of radio galaxies are elliptical galaxies. Elliptical galaxies. Now, you can ask yourself the question that quasars were discovered by a radio means. All right, fine. Quasars are also copious emitters of X-ray emission, originating from the accretion disk around a supermassive black hole. If X-ray astronomy had started before radio astronomy, you'd have probably discovered quasars via their X-ray emission rather than their radio emission. They're very copious emitters of the X-ray. But suppose I took a volume of space and counted all the quasars over there and tried to see how many of them are powerful radio emitters. I can also do that for a volume with all kinds of elliptical galaxies and ask myself the question, are all elliptical galaxies giving out jets and forming these fields? The answer is no. Okay? The answer is no. Only about 10% of all elliptical galaxies seem to be luminous radio sources. And similarly, a ballpark number, if I look at all quasars in a given volume of space, only 10% of them are extremely luminous in the radio. All right? But what we do notice is that when they're radio loud, they're usually associated with ellipticals, and when they're radio quiet, they could be spirals or ellipticals. Okay, and that is what this slide shows you. So there seems to be a relation between how luminous a source can get with the associated optical object. Okay. I've just written down the kind of luminosity. These are very ballpark numbers. When I say radio quiet, as I mentioned, that they're radio weak but not radio quiet completely, but this is the terminology which continuously tends to get used. This is just a summary of what we have done so far. Seyfert galaxies, 1, broad lines, 2, narrow lines. Radio galaxies, usually narrow lines. There's some broad line ones which we will ignore for the time being. Quasars, broad lines. And there is a class of objects called BL-like objects, okay, which I will briefly mention only. These were also found by looking for optical counterparts of radio sources. They were also star-like. In fact, BL-like gets its name from a star which is classified as a variable star. Variable stars are usually named by the constellation in which they occur, and then they have combinations of letters A, B, etc. Till they run out and they put a V and a number after that. Okay, so BL-like objects are BL-like objects. They usually have very weak emission lines or no emission lines at all. So that is what is shown over here. We'll tie all this together later. So BL-likes will come over here. All right, they have weak or no emission lines at all. Weak or no emission lines. So this is sort of the zoo of active galaxies that we'll discuss today. Right? Right. Now let me see. Okay. Now what is the kind of luminosity that we're talking about, and what are the kind of sizes? What are the global properties? They can be very small. Very small means how small? From less than about a few parsecs or so is what we have imaged. 1 parsec is about 3 light years, to sizes which can go up to megaparsec scales, millions of parsecs. So they start off young from the nucleus of an active galaxy, and they keep growing as the jets move through, initially through the interstellar medium of the host galaxy, and later through the, if it's in a cluster, the intercluster medium, or the general intergalactic medium. Luminosities I've written down over there, some ballpark numbers at 1400 megahertz. And you can ask yourself how old they are, and their ages usually. You can measure by different means. We illustrate a little bit of modeling to you in a short while. But for the very compact objects, you can actually monitor its motion and then find out that if they originated in a point, how young they are. For the large sources, it's difficult to do that, but in the young sources where they're compact hotspots, you can do that. And ages range from less than a few hundred years to over 100 million years. So that is the time scale for the largest objects, several hundred million years. And these objects actually are very important not only to understand their evolution itself with time, but they can have a profound effect on the evolution of the universe itself. because as the jets go out, they're going to affect the host medium of the galaxy, they're going to affect the intercluster medium, and and uh, and they can profoundly affect the properties of the host galaxy, the ICM and the IGM, as they interact with it. And this is going to affect the subsequent evolution of other galaxies and the intergalactic medium or the intercluster medium as well. Now, having looked at the global properties, remember they can be very small to very large as they evolve, and the luminosities are about 10 to the power 20 to 29. Okay, I've shown you linear sources so far, but when they occur in a group or a cluster, the parent galaxy can actually be moving around the cluster as well. Clusters usually contain a dominant galaxy at the center, but there are other galaxies which can have high random motions of even thousands of kilometers per second. So you can see that when they're in a cluster, they can have all kinds of interesting shapes where ram pressure bends the tails of the cluster. Sometimes you have galaxies which have two supermassive black holes in them. They will possibly merge at a later date, and both of them are active, spewing out jets in this particular galaxy. Not too many examples of this type, but there are. Jets can also start precessing. For example, if a black hole is disturbed for some reason by an interaction or so, and some of these, this is not the best example, but it has been modeled as precession of jets as well. So jets can precess, they do not remain linear. The other aspect I want to highlight before I come into a little bit of the physics is that I talked about radio quiet and radio loud objects over here, okay? And one question to ask oneself is, which is also going to affect the way we look at the universe, is that suppose the jets have come out. Do they just live for 100 million years and then die off? Or do they actually keep rejuvenating itself? Suppose there's a new supply of fuel to the black hole. Suppose this fuel supply is intermittent. So these are examples of recurrent activity. This is a GMRT image which we had made many years ago, and we can also look at time scales of episodic activity to see what effect this might have on the overall properties of the galaxy and the medium in which it resides. And when I talked about modeling, I just wanted to draw upon what Dipanjan talked to you about yesterday, that when I do a spectrum over here, okay, that if there is no energy loss at all, and it starts off with a non-thermal spectrum, it is going to have a straight line. But as Dipanjan pointed out yesterday, that the higher energy electrons are going to lose energy faster, isn't it? Proportional to E squared, right? E perpendicular squared. So let's just look at E squared. So the higher energy electrons are emitting at a higher frequency, right? Via the synchrotron process, and they're also going to lose energy faster. So what happens is that with time, this spectrum is going to, unless there is a fresh supply of electron or reacceleration, is going to keep steeping. Okay, going to keep steeping. And where the frequency at which the steepening starts is going to go to lower and lower frequencies as the source ages. Okay, so from looking at the spectral break, you can go and estimate what the source size is. Here, for example, in the central object, you see a straight spectrum over the frequency range over which you could measure it, but whereas for the diffuse outer lobes, you can see that it has begun to steepen. And from this, we had estimated a spectral age of about 2 million years for the younger ones and about 150 million years for the older one. So that provides a tool. There are caveats, there are assumptions, but at least it provides you a ballpark figure of how old the source is. This recurrent activity, usually one sees 2 pairs of lobes, sometimes you can see 3 as well. This was something which we had found with the GMRT as well, and just to give you an illustration of it. Recurrent activity can also be actually probed via X-ray observations. Yesterday, I think Chomak showed you, or was it Dipanjan showed you, the X-ray imaging from a cluster of galaxies, which is thermal brainstorm free emission, right? From hot gas, which could be several million degrees Kelvin. Now, what happens in this hot gas if you have plumes of radio plasma going out? It's going to actually displace the plasma over there, right? So what you see are cavities where the radio emission is. And sometimes you go and see cavities which are not one pair of cavities, but multiple pairs of cavities, which gives you another handle on trying to understand recurrent activity in active galactic nuclei. So we will not spend too much time on that, but just to illustrate to you that sources are born young. They start off, plowing its way to the interstellar medium of the host galaxy, and then to the intergalactic medium, intercluster medium and intergalactic medium. And if there is no fresh energy supply, they will just decay on a given time scale of several hundred billion years. And this is one of the sources where you can see right now there is no fresh supply of energy. So you can actually see a hole in the center over here where energy has been lost. The core is still visible, so it may become active at a later stage. So recurrent activity is something which is quite common, but is it there in all galaxies? We don't really know. I think we have to do far more observations, particularly at low frequencies, to try and detect an emission. So this is just to give you a summary of the kind of scales that are involved for these sources. There are sources, as I said, which are far smaller, less than a few parsecs, but this is Cygnus A, which we talked about, Hercules A that we talked about, which is about 120 parsecs, 600 parsecs, to the largest objects, which are close to about 5 megaparsecs or so. Now let's ask ourselves a few questions, okay? Now, a few questions. Now, before we ask these questions, I'll keep an eye on the time. Maybe we started a bit late, another 20-25 minutes will finish, all right? Now, do you have any questions on what we have discussed so far?
So there is some high energy cutoff at what you have shown that.
I have drawn the radio spectrum over there. Okay, the radio spectrum over there. For example, that is the radio spectrum over there. Yes, it cuts off because the high energy electrons are radiating away their energy far more rapidly than the lower energy electrons. So in a given time scale, if there is no reacceleration of the particles and there is no fresh supply of electrons, then the spectrum is going to steep slow. But on the other hand, if there is a fresh supply of electrons or there is reacceleration of the particles over there, then you will not see the spectrum.
So this will be different for different type of galaxies?
This could be different for different sources, not necessarily for different types of galaxies. It could be different for different types of sources. For example, if I look at the jets, where there's a lot of interactions going on, where the particles are generally young, I can detect jets right up to the optical or the X-ray region of the spectrum. Some of these jets, I can plot the spectrum, the non-thermal spectrum, starting from the radio to the X-rays, and I find the straight non-thermal spectrum. That means there are highest energy electrons which are present in these jets, which are radiating in the X-ray region of the spectrum. They will have a much shorter lifetime than the radio frequencies. So unless these electrons are being continuously replenished, the spectrum is going to steepen very rapidly. But there are a large number of jets which have been detected at X-ray wavelengths, and there's also signs that at gamma ray.
Quasar will have higher.
Sorry?
Quasars.
Yeah.
They will have higher cutoff because it is going in optical.
No, you also see some of the jets in galaxies in the optical, but quasar jets in X-rays are far more common than in the optical. That is true, right? Any other questions? Yeah, go ahead.
In the X-ray image that you showed,
In the
X-ray image that you showed,
yeah,
you were trying to make the point that the regions where there is no X-ray emission, there if you even look in the radio band, you will see dominant.
there is, yeah, because what happens is the radio emission, the radio lobes of emission, it displaces the X-ray emitting gas. So you don't see no X-ray emission, but you see less X-ray emission. So it's like holes or cavities in the X-ray emitting region. Okay, and you can infer. I mean, you can also do work of how much energy is required by the radio emission to displace that, the work done and calculate the energies in the jets themselves. But you can also look at multiple pairs of cavities in some. I didn't get a good image right now yesterday when I was putting this together. But there are also sources where you see multiple pairs of cavities showing that the episodic signs of episodic activity can also be inferred from X-ray observations. Right? Okay, now we'll go ahead. What is the total energy content in the lobe? How is this energy generated? What are the velocities involved? Okay, so we'll try and go through a little bit more rapidly, but feel free to actually stop me at any point and ask a question if you wish to. All right. The famous image of Cygnus A. Luminosity, as you can see, is quite high. This is integrated over the radio region of the spectrum, roughly, and originates from the parent galaxy. And using synchrotron theory, if I calculate what the total energy content of the lobe is, is of the order of 10 to the power of 60 to 61 ergs. So it's a huge amount of energy, and the typical magnetic fields in the lobes is on 10 to 100 microgauss, or even lower in the more diffuse lobes. Cygnus A is one of the more luminous sources. It has a higher magnetic field as well. Now, we'll go and sort of discuss what is the source of this energy, okay, without getting into too much of detail. And what is believed to be the source of energy is nothing but gravitational potential energy, right? I mean, if I take this chalk and drop it, I mean, it is going to build up its kinetic energy. At the cost of its potential energy, gets more negative and becomes more tightly bound, but suddenly stops and hits the surface. So what happens to the kinetic energy? Okay. Now, this kinetic energy can be used in all kinds of things. For example, certain kinds of vultures are known to drop, bones from great height to break them. Eagles actually drop turtles from great height to break it and get it to me. But these particles, masses of protons, or masses of protons or a cloud, which is hitting it, okay, is believed that most of it is radiated away as heat, right? The kinetic energy is radiated away as heat. And when you look at the efficiencies of these processes, I've just written down, you can just do the simple calculation yourself and get it. It is just half mv free fall squared is equal to gmm upon r, and you can differentiate with time, and half m dot c squared, you can equate it to the luminosity and calculate the luminosity over here. I've just expressed it in terms of the Schwarzschild radius. Rg is equal to 2gm by c squared, which Shomuk introduced yesterday. And you can see that the luminosity which you get over here depends on the rate at which mass is accumulated and the ratio of Rg upon R. Okay, Rg is 2gm by m squared. So the more massive the object is and the smaller the radius is, you'll get this factor to be larger. And you can think of this factor as some kind of efficiency of the conversion process. And when you have a neutron star, which is about 10 kilometers in solar mass, you'll get a much higher rate of efficiency compared to even the proton-proton chain, which is responsible for energy generation from the sun. So gravitational potential energy provides an efficient process of extracting energy to supply the large volumes or large amount of energy that we see in these globes. Okay? Ask your question, can we keep increasing dm/dt infinitely to get very large luminosities? What do you think? I keep increasing dm/dt and I keep getting larger and larger luminosities. Is there a limit, or can it go on and on? There's a limit. What does the limit arise due to? Radiation pressure. Very good, excellent. Okay, excellent, very good. Okay, okay. Before we get into that, this was what Shomuk talked about yesterday, that matter starts with a certain angular momentum, and conservation of angular momentum means it will go more and more rapidly as it gets closer and closer to the center. The rotational energy varies as 1 upon r squared, whereas the gravitational potential energy changes as 1 upon r. So unless you can actually dissipate the angular momentum, it will never get to the center, right? So, but what gets dissipated is that because of the viscosity in the material, it forms an accretion disk around the compact object, okay? Which is what Shomuk talked about yesterday. Viscosity acts as a frictional force. It redistributes angular momentum, taking some of it outside, allowing some of the material to fall inside, and generates sort of energy. And friction also generates, leads to generation of heat from the accretion disk. So if more detailed calculations, which I'm not going to do over here, is that if you have a Schwarzschild black hole, which is basically a black hole which is non-rotating, okay, a non-rotating black hole, the efficiency is about 0.06, whereas if you have a rotating black hole, again, the efficiency depends on whether it's prograde or retrograde motion relative to the spin of the black hole, but you can get for prograde motion as high as about 0.426, okay? And you can see that this is the most efficient way that we can actually generate energy or extract energy to supply the kind of energy that we see in the lobes of radio galaxies and quasars. And as you answered, there is a limit to it, and that's because of radiation pressure. And this luminosity was calculated by Eddington, and is known as Eddington luminosity. And it basically depends only on the mass of the object. So the higher the mass, the higher the Eddington luminosity that you can get. And usually we find that most of the objects, almost all objects, the luminosity that we estimate is within the Eddington limit or close to it. So we have shown that we have shown that accretion provides a viable process to account for the energy as the most efficient process. We will not get into details of the generation of jets. There are clever processes by which magnetic fields play an important role in collimating the flow, but we will sort of skip that for in this lecture. But you should just be aware of it. Okay. Now we'll look at the velocities of the jets. Okay. The energy we decided was that accretion provides the most efficient process of extracting energy to supply energy to these huge lobes of emission, which could consist of about 10 to the power of 60 ergs or so of energy. Now the next question we basically ask ourselves is, what is the velocity at which these jets are going out? And can we understand their asymmetry, which we talked about earlier? Particularly for the Van der Waals class resources, we saw that the jets are generally tend to be very asymmetric compared to the Van der Waals class of objects. Let's look at that a little bit. Now this is in response to your question that you can see these jets in a galaxy as well at X-ray and optical wavelengths. So, and in this particular source, it has been modeled pretty well as a spectral energy distribution from radio to X-rays is due to synchrotron emission. All right. So that, but that is not always the case, and we will see that in the case of the quasar, that you need to invoke inverse Compton scattering as well. There are also issues with that, but details we'll not get into. But inverse Compton scattering is what Devanjan talked about yesterday. And if you remember that that inverse Compton scattering, the scattered photon nu prime is of the order of gamma squared nu. So if I took this electron, this frequency of 10 to the power of 9 gigahertz, okay, 10 to the power of 9 hertz, sorry, 1 gigahertz, and gamma squared is 10 to the power of 4, so 10 to the power of 8. So nu prime would be about 10 to the power of 17 hertz, which will take you into the X-ray region of the spectrum. So inverse Compton scattering, where the photons gain energy at the expense of the relativistic electrons, also provides a viable way of trying to understand the high frequency emission from these jets at X-ray and gamma ray wavelengths. Okay, so for modeling, one has to take that account. Now, which plays a more important role? That depends on the photon energy density versus the magnetic energy density. Okay, but I just want you to be familiar with the process. Now, how fast are the jets moving? How do we measure it? We can measure it provided we find a compact knot on VLBI scales, because the motion is very small, it will be only in milliards second level. So I need to be able to observe knots of emission in the jets at milliards second level. If there are diffuse structures which get resolved out, I'll not be able to do it. All right. Now here is a jet made with a very long baseline array, which I think Nassim showed you an image of in the first lecture. And and if you can follow, for example, the motion of this knot relative to the nucleus, you can go and estimate what the velocity is. You know the distance it has traveled, you know the time it has spent, and you divide the distance by the time, you get a velocity. But the surprising thing which came about when it was first noticed or first worked out in the 70s itself, that the velocities turned out to be much greater than the velocity of light, very often. So it went by the name of superluminal motion. In the early days, when most of the astronomers were actually optical astronomers, people didn't take it very seriously. They said the radio astronomers were called Moore, then very derisively referred to as the wire welders of astronomy, that they must have been cooked up somewhere. So velocity of light, Einstein's theory cannot be violated. But a very clever explanation was actually put forward by Martin Rees. I will just try to illustrate that to you, and without actually getting into too much of detail. All right. This is also another image of M87, where superluminal motion has also been inferred from optical wavelengths. Now, what you see over here is that if I have a knot in a jet which is coming towards me, all right? Say there's a knot which is coming towards you. How would you measure the time difference? You would measure time difference at, say, two different locations of the knots. Let's say you measure a time interval when the knot has just started off from the nucleus. All right? There's a wavefront which is emitted, which will come to you at the velocity of light. And the knot which is coming is also traveling. Say after a certain time t, there is another pulse of emission. Okay? And this is what is sort of illustrated in this figure over here. Now, how will you measure the velocity and the distance? Now what you see over here is whatever you see would be projected onto the plane of the sky, right? And let's say this jet is inclined at an angle phi to the line of sight. So this distance it has traveled is Vt sine phi. Now the time which you are going to measure is the time between the wavefront which it emitted here versus the earlier wavefront which it has been traveling towards you. So the time scale you infer is this distance divided by the velocity of light. So if you divide this by this distance divided by the velocity of light, this is the expression which you will get. So what basically happens is because the knot is almost traveling close to the wavefront at a high velocity, the time interval which you measure gets squashed. So distance divided by time is what gives you an apparent velocity which is greater than that of light. So there is no information which is being transmitted at a velocity greater than light. So there is no violation of special relativity at all. It's a geometric effect. Now, geometric effect, and so when will you see superluminal motion? You'll only see superluminal motion when an object is coming towards you or at a small angle to the line of sight. If it is going away from you, you're not going to see it. If it's at a large angle, you're not going to see it. So whenever you see superluminal motion, it means that the object is at a reasonably small angle to the line of sight and the knot is moving at a velocity which is pretty high, not very far off from the velocity of light. Now we talked about the asymmetry of jets earlier. Now what happens again, which Devanjan talked about in terms of the lobe of emission being in the forward direction, but the solid angle transformations and also the fact that the observed frequency and the emitted frequencies are different, the observed bandwidth and the emitted bandwidths are different. If you figure all that in, what you get an expression is that the observed intensity is given by the intrinsic intensity upon gamma G. Gamma G I put over there to distinguish it from the Lorentz factor of the individual electrons. This is the gamma factor which corresponds to the bulk motion of the knot or jet. Right? That's why the subindex J over there. 1 minus beta cosine phi to the power of n plus alpha. N is sort of model dependent. If it is going away from you, it will become a plus sign over here. Right? If it's coming towards you. Now you can see that when the object is going at a high velocity at a small angle, this is going to be small, and you can get very large values of the observed flux density. Okay? And this is just Doppler boosting. But on the other hand, if it is going away from you, then it's a plus sign. This is going to be a large value, and you're going to get a diminished flux density. So if you see a highly asymmetric jet, what you infer is that the jet is coming towards you. Okay? And the one which you don't see is going away from you. If the velocities are very small, then that effect will not be there. Okay? And even if you have sources at a large angle, if I put phi equal to 90 degrees over here, then I will get what is the transverse Doppler effect, which S observed is equal to S intrinsic divided by gamma to the power of n plus alpha. So n is either 2 or 3, which is a little bit model dependent, but you can see the flux density is going to decrease. So when you see asymmetric jets, it implies that you're seeing sources which are inclined at a small angle to the line of sight towards you. Right? Is that clear? Yeah? Okay. I'll probably, this is the same thing which I'm saying over here, that the velocity is c and phi is about 20 degrees and the flux density ratio is in the thousands. So this explains the asymmetry of the jets over here. Okay? Asymmetry of the jets over here, which we saw in these objects over here. Here it appears symmetric because these low luminosity jets are far more dissipative. When you look at it, they're very close to the nucleus. Then they start off at a high velocity, but they slow down very rapidly. And that is why, because the velocities are low, you tend to see that they are reasonably symmetric. Okay? Okay, I'll take another 10 minutes and then I'll probably stop. All right? Now, this I will probably skip, I think. Okay? If there is time later, I will come to it. There was an interesting test of this which was done. And this is just an illustration of very detailed modeling which has been done by Robert Lang and Alan Bridle and the collaborators, which sort of shows you the velocity profile of even an FR1 jet, which I mentioned a little while ago, that it starts off very close to the velocity of light. This is 1 over here, V by C, and then it slows down quite rapidly. Whereas in these jets over here, the FR2, it doesn't slow down as rapidly, and even on large scales, you see them well collimated and with higher velocities than in the low luminosity jets. Okay. So I'll spend 10 minutes of my time to just illustrate to you, put together whatever we have learned today and how that actually helps in terms of understanding diversity of the zoo of active galaxies or active galactic nuclei. So what have we learned so far? We have said that radio cores are flat spectra and that can be resolved into nuclear jets. Superluminal motion when nuclear jets are inclined at small angles to the line of sight. Nuclear jets are moving at close to the velocity of light. Flux density of approaching jets are Doppler boosted and receding jets are Doppler diminished. And all the superluminal sources tend to have more prominent radio cores and are often variable, and that is because of their small angle to the line of sight. More asymmetric jets in sources inclined at small angles. Okay. So this is sort of a brief summary of what we have been talking about for the last 10 or 15 minutes. So is there any question on that? No? It's clear to everybody? Yeah? So I will build upon that for 10 minutes and then we will stop. Okay? Now, let's look at these two objects over here. Alright? On the left, I've shown a radio galaxy. Okay, typical radio galaxy. On the right, I've shown a quasar. Okay? A quasar. So we have looked at this equation that when the source is inclined at a small angle, its flux density gets boosted. And the core, because of optical thickness effects, also has a flat spectrum. So here you can see the emission is dominated by the nucleus and the spectrum is flat, right? So I will say that this object actually also exhibits superluminal motion, such objects. And so it is an object which I can safely say that with the available information, it is inclined at a small angle to the line of sight, all right? Here, this object, 3C452, is associated with a galaxy, all right? Associated with a galaxy. I don't see a prominent jet at all. It's not dominant. There is a core you can detect, but it doesn't dominate the emission at all. It's a steep non-terminal spectrum dominated by the extended lobes of emission. The fact that I don't see a prominent jet, I could say that if it is because of the Doppler effect, it is inclined at a large angle to the line of sight, right? So what I'm saying over here is that the quasar is inclined at a small angle to the line of sight, and the galaxy is inclined at a large angle to the line of sight. Okay? Can I extend this further to say that perhaps galaxies and quasars, if the extended radio structure is the same, are the same objects, but we are seeing them differently. Right? They're the same objects, but we are seeing them differently. But I cannot actually mix up the Van Raaphorelli class 1 and 2 because one which doesn't have a hotspot, if I turn it around also, it's not going to generate a hotspot, right? But if the extended structure is similar, then can I actually say, so for example, if I take all Van Raaphorelli class 2 quasars and Van Raaphorelli class 2 galaxies, can I say that they are absolutely same, but they just are inclined at different angles to the line of sight? Okay. So let's try and probe if that information is correct, right? After all, I can say anything, but to make it, it's maybe consistent with one set of facts, but is it consistent with a broader set of facts? What is a broader set of facts? The emission lines. Quasars have broad emission lines, galaxies have narrow emission lines. So how do I reconcile the fact that the radio information tells me that, Baba, they are the same objects inclined at different angles, but I see optical emission lines which are very different. So I have to understand that, right? So let's see if we can understand that a little bit. Here actually in some of these objects, you don't see the extended emission because of dynamic range limitations. When you look at them with much deeper dynamic range, you pick up a lot of the diffuse extended emissions, except with low emission as well. Okay, so this is what we are trying to say now. You all told me in the beginning that the broadline region has to be close to the black hole, right? Why close to the black hole? Because it has large velocities. Just like Mercury moves much faster than Jupiter, right? So the effect of the gravitational influence will lead to the broad emission lines being closer to the nucleus. All right. So this is what this cartoon actually shows you. That these are the broad line region over here, okay? And these are the narrow line regions over here. Okay. Now let me just look at FR2 radio galaxies, okay, for a time being. Among radio loud objects, if I see an object along this side, and there is a supermassive black hole, there is an accretion disk, and there is a torus of material, which we'll come to in a moment, surrounding that structure. Now, if I look at the object from this angle, narrow line radio galaxy, I'm not going to see the broad lines. Okay? I'm not going to see the broad lines. Whereas if I look at the same object from here, I will see the broad lines and it will appear as a quasar. Okay? Now, similarly for the FR1 objects, if I see it here, I will not see the emission lines, but in the BL-like objects, I should see the emission lines, which we said have no emission lines at all, or very weak. What is happening in the BL-like kind of objects, they're really extreme. You're seeing right through the throat of the outer jet, right? And what happens is that if I had an emission line spectrum, which looked like this, in a BL-like object, so let me see it has weak emission lines. I have a continuum as well. But if I actually Doppler boost the continuum to a level over here, I'm not going to see the emission lines. So the beaming effects are very severe. The objects are so strongly variable and bizarre that they have been called Quasars. Is another nomenclature which gets used. So BL-like FR1 galaxies, the unbeamed or large angles to the line of sight are the BL-like objects, and the radio galaxies are the quasars. Similarly, which we talked about, the Seyfert galaxies, right? The Seyfert 1 and Seyfert 2. Large angles, here you can see over here. Seyfert 2 is when you don't see the narrow lines, the broad lines, because obscuration by the torus. And Seyfert 1 is where you can see the broad emission lines. So it is a geometrical construct now, okay? Now, if I want to really convince you, I have to tell you that this has to be correct, right? I mean, I put in an arbitrary torus over there. You say, what the hell? You know, how do you know it exists, right? So, what is the observational evidence I can look for? Okay. So, right from the black hole over there, with the accretion disk, there are photons which are coming out, right? Photons are going to ionize gas in this vicinity. Now, if the photons are going out in 4 pi steradians, then it's going to ionize gas all around it. But if it is a torus, like a donut or a minibara, all right, then it's not going to go out in all directions. It's going to go out where there is a path. So I should be able to see cones of ionized gas as observational evidence that Baba, this picture may be correct, right? May be correct. And there have been, I'll just show you a few examples because we're running short of time, okay? This just summarizes the same thing about type 1 and type 2, which we discussed a little while ago. Yet you can see this beautiful ionization codes. This is a Seyfert galaxy. These have been done in more detail this is right from the nucleus of the galaxy. This has been done in more detail for nearby galaxies because it's easier to do it. And they're often asymmetric because of obscuration effects and all that, depending upon how the galaxy is inclined. And this is just not an isolated example. There are many such examples. And it has also been done for radio galaxies. Okay? As well. So far, so good. Okay? But the clinching evidence would be, let me see. Okay, this is another one. The clinching evidence would be that if I can prove that there is indeed a Seyfert 1 nucleus hiding over there, isn't it? I mean, this gives me a reasonable picture of a torus over there. All right? A torus which is obstructing photons going out in 4 pi steradians, and I can see the ionization codes. So it tells me, that this broad picture is correct. I mean, we still have issues about how this torus may have originated, and there are very clever ideas about it as well. It may be winds from the disk contributing to it, but those issues we'll not get into. We'll just look at the wide diversity and whether what this is telling us, okay? Whether some of it can be due to geometrical effects of orientation and relativistic motion. But how would you find out actually? I mean, imagine that suppose I'm quiet and not speaking, and there's a screen between me and you all. How do you find out that I'm here? I'm quiet, and there's a screen in front. How are you going to find out? Sorry?
Thermal imaging.
Sorry?
Thermal imaging.
Thermal imaging. I said there's a screen and there's no radiation going through. The answer is a mirror, right? Suppose you had a mirror somewhere. Suppose you had a mirror over there, right? Then you will see me, isn't it? So can I have a mirror in the galaxy to reflect the hidden nucleus from me? Right? Can I have a mirror? So we talked about the interstellar medium briefly, and we talked about clouds of electrons, clouds of dust, Thomson's scattering radiation. And if you're lucky, it may scatter into your line of sight. It can scatter in any direction, but it can scatter into your line of sight as well. And what is the signature of it? Signature of it, scattering also produces a degree of polarization, right? So usually for broad lines, I will not be able to, I need a massive body. I can't just generate broad lines very far away when there's no massive body. So if I see broad emission lines, which are polarized, it's quite likely that that light is reflected light from a hidden secret or type 1 nucleus. Right? So this is what is it's very painstaking observations. Initially it was done for NGC 1068, which is a classic C42 galaxy. That means it has narrow lines only. And the question was, does it have a broad line nucleus? This was done by Saikia and others, and now it has been repeated for many other objects. So intensity you can see over here, the bottom line, you can see this broad emission line which is polarized. Here the polarization sort of contours are plotted over here, but this is sort of gives you in a cartoon form it is showing you over here that if you can actually go and see the nucleus over here, this type 1 nucleus reflected into your line of sight. It's a cartoon by Sulfan which is plotted. So what you can see over here is that we have built up a reasonable amount of observational evidence to not only understand some of the physics of these objects, but also that the diversity of active galactic nuclei can be understood, at least some of them, in terms of orientation and the effects of relative distribution. So this is still an active area of research, and people keep testing it all the time. It's a fair degree of success in explaining a wide range of observations, but there are still questions: how does a torus form, role of winds, role in the collimation of jets, where does a jet get collimated, does it have a spine and a sheet, what are the constituents of the jet, is it proton, is it electron positron, is it proton electron? So these are issues which we are still sort of trying to work on. And today with actually improvements in observations, not only with the Event Horizon Telescope, but global millimeter wave VLPI, which also gives resolutions at tens of microarc-second levels. We are trying to get closer and closer to the regions, closer and closer to the structural radius, to try and understand how jets may collimate, how does energy get transported, is it Poynting flux or is it particle flux? Does Poynting flux get converted into particle sort of energy later? So these are issues which has to be led by observations, and we are making sort of dents in it. But today's lectures is sort of just giving you a broad introduction to active galactic nuclei, specifically on radio galaxies and quasars, illustrating examples of sources of energy, emission processes, and understanding the wide diversity of active galactic nuclei in terms of orientation and relativistic medium effects. So we'll stop here. I overshot by about 10 minutes, but I could take questions, some questions now, and we can discuss about T as well.
So why do you say the stars have the absorption spectra? I didn't get the reason which you said, because they are also emitting radiation.
Which one?
Stars.
Yeah.
You said we get the absorption spectra for them.
Okay. What happens with stars is that if you look at the star, what you have is the inner photosphere. All right, inner photosphere. Okay, this is the photosphere, and what you have is a cooler outer layer. Cooler outer layer. So what you, for example, if you had a source of emission, over here and say it is black body, all right? Black body. Now, what is going to happen is depending upon what elements are over here, you're going to see, based on its thermal spectrum, you'll see absorption lines corresponding to the species. Right? This was what actually Fraunhofer found many, many years ago. That if you, for example, if you didn't have this cooler outer layer, you would see the continuum emission. But because of the cooler outer layers of the photosphere, it absorbs light depending upon the elements that are present over there. And that was one of the very important sort of findings, right? Because when Fraunhofer actually, he noticed several hundred of these very dark bands in the spectrum. And people identified many of these to elements which are found in the and that is why in the very early days there was widespread belief that the sun is made out of material which is terrestrial, which is very close to the composition of the earth.
So like these stars don't form like because in sun as we go away from the photosphere the temperature increases.
As we go
Away from the photosphere the temperature increases from the chromosphere.
that is another aspect of it. It's a question of what as you go away from it, the corona is very hot, right? Corona is 1,000,000 degrees Kelvin, and I think the energy supplied to the corona from the surface is what keeps what heats the corona to a very high temperature.
So this does not follow from like normal stars also. Like this is a special feature of sun we're talking about. It does not like for the general solar population this is not true.
No, this is true of all stars.
Like we are saying here it's a cooler outer layer.
That is true of all stars.
The sun also.
All stars are characterized by absorption spectra. I mean, there are exotic stars which are prominent emission lines. The Wolf-Rayet stars, for example, where you see prominent emission lines as well. But generally, the classification of the spectra of stars is based on the absorption lines, and what lines you see depends on two things. One is, for example, I'll just spend 2 minutes on it. Okay, that spectral classification of stars is based on the spectra which have been taken at optical wavelengths. Okay, now depending on two aspects. One is the temperature of the star. Okay, temperature of the star basically, which depends on the mass as well, determines the kind of spectrum that you will see. All right. For example, if I take the sun, okay, let me take Vega at one end and let me take sun at one end. Vega is a hotter star than the sun, right? Vega has very prominent lines of absorption lines of hydrogen. Okay, the sun, which is a G-type star, which is cooler than Vega, have absorption lines of various elements. It has much weaker absorption lines of hydrogen. It shows some lines, but it is much weaker. Now you can ask yourself, and if you look at, for example, much cooler stars, like for example the M-type stars, okay, they are much cooler. Now to see an absorption line, okay, for example, when I look at absorption lines of hydrogen, they are absorption lines from the n equal to 2 level, right? N equal to 2 to 3, 2 to 4, etc. Right? The Balmer lines, right? Now I will need to have energy. The star will have to have energy to put enough electrons into the n equal to 2 level. All right? Now in the sun, for example, the actual strength of the line depends, which Cecilia Payne-Gaposchkin was the first to work out, depends on the level of degree of ionization of the material, plus, which is given by Saar's ionization equation, and the population levels at different energy levels, which is given by Boltzmann's equation. Now, if I take the sun, then there are not enough electrons in the n equal to 2 level to give you enough strong lines of hydrogen. But on the other hand, an A-type star like Vega, it is much easier because of the high temperature to put electrons in the n equal to 2 level to see very prominent lines of hydrogen. Now, if I go even stronger stars, which I think somebody talked about earlier in the lectures, O-type stars, which are 20,000 degrees Kelvin, there actually you will not see again hydrogen because hydrogen will be completely ionized. So you need electrons at a proper level in this cooler outer layer to give you the right kind of absorption lines. So stellar spectra is basically depends on the kind of absorption lines you see. If you take an M-type star, there is no hope of getting enough electrons into it. In fact, you see molecular lines over there because it is out of cooler atmospheres over there. Okay.